Welcome. It's a great pleasure to be here and to tell you about quantum networks. And the specific focus will be on how we can take this early stage technology, which essentially is a physics experiment, ultimately on the path towards a network system. And most of my talk will be an overview about this exciting new field, and I'll conclude with some super recent results from our lab on the implementation of the world's first link layer protocol. So when you hear about quantum networks, you quite often hear that we would like to bring in entanglement to everyone and ultimately enable quantum communication between local quantum processors anywhere on Earth. So this is a very lofty and difficult to attain goal. And of course, the first question that arises when one talks about it is, why would anybody actually want to do that? So when we send classical information, we transmit bits, 0 and 1s. And when we send quantum bits, we send something that in some sense can be a superposition, a 0 and 1 at the same time. And these quantum bits have some very exciting properties that enable totally new applications. One of the most famous applications of quantum communication is secure communication. So here, quantum communication is used to distribute an encryption key between two nodes on a network in such a way that even a quantum computer cannot break the security of this key now or in the future. So this also protects against the fact that someone might record actually communication that is happening right now and use a larger quantum computer in the future to break it. However, quantum communication has many other applications, for example, secure quantum computing in the cloud. So this means that one would use a simple client device to access a powerful remote quantum server, for example, in order to simulate a proprietary new material. And the objective of this secure quantum computing in the cloud means that we want to do this in such a way that the server can actually not know what the client wants to compute, in particular, what that proprietary material would be. Many other applications are already now, some quite diverse, ranging from clock synchronization, password identification, position verification, even to cheating, using quantum entanglement to cheat at online games. Quantum networking is not only interesting at long distances, but also at short distances in order to build a quantum computing cluster out of smaller quantum computers. So the idea here is essentially exactly the same as in a classical domain of how one can build one larger, more powerful computer from several smaller ones. So when you hear about these applications, there's maybe now a question in your mind is what is it about, what makes quantum bits so special to enable these futuristic applications? And there's essentially two properties of entanglement that might give you some intuition of why quantum communication can be useful, or in general, actually, what quantum communication can be good for. So the first property of entanglement is sometimes what I like to call maximum coordination. So if I have a qubit here in Delft, you have one at home, and they're entangled with each other, and I make a measurement on my qubit, which you can think of as posing a question. For example, are you pointing left or right? Then if you make the same measurement, you get the same outcome, even though that outcome is not determined ahead of time. So in other words, if I see left, you also see left. If I see right, then you also see right. So the outcome is probabilistic, it's not determined ahead of time, but it is always the same on both sides. The second property of entanglement is that it's inherently private, because you might have just thought, this is very nice. Maybe it's possible to have equally strong entanglement with many nodes in a network. So it turns out that this is actually fundamentally impossible. So if our qubits are completely entangled, fully entangled with each other, then it's physically impossible for anything else in the universe to have any share of that entanglement. In that sense, entanglement is inherently private, it forms a private connection that one can also test in order to rule out eavesdropping. Okay. So before I delve into some more details actually later, let me first give you a little bit of a cartoon of what a quantum network looks like. So quantum network on a high level essentially looks very similar to a classical one. So we have something which we like to call end nodes. So this is a computer or a phone that you connect to the network on which the applications are run. In the quantum regime, these can be very simple devices that can just prepare and measure one qubit at a time, but to much more complicated devices that might be capable of storing and manipulating several quantum bits or qubits at once. All the way, of course, to imagining connecting eventually a full-blown quantum computer. In order to do quantum networking over long distances, we also need something called a quantum repeater. And I'll say a bit more about later why it's actually challenging to make one and how a repeater could work in the future. And of course, you might have been wondering, how do all of these devices actually talk to each other? So this can be done in a variety of ways, in particular also in standard telecom fiber that actually is already in the ground right now. So if you're interested in learning more about what you can do with such a network, and in particular also when you could maybe do what user applications, we've introduced a few years ago now functionality-driven stages of quantum Ethernet development. So these are stages that are defined purely from the perspective of what value can the network actually deliver to the user. So what can the end nodes actually do? So the first sort of true quantum network is what we call a prepare and measure network, where every node in the network can prepare a qubit. The network is capable of transmitting the qubit to a desired receiver in the network, which can either correctly measure it or a signal is produced that says that transmission is lost. We can imagine more complicated networks that actually generate entanglement between them, which is actually a natural way to bridge long distances, as I'll explain later, to quantum memory networks, where you have actually little quantum processors connected to the network that are still noisy, but one can indeed already do very interesting things with them. So I would like to emphasize that actually in quantum computing, where of course the objective is to be better than what a classical supercomputer can do, already a small number of qubits, in fact even just one at each end node, can already do things that are classically impossible. And this comes from the fact that network applications derive their power from quantum entanglement that cannot be simulated using classical communication. And such entanglement can already exist between two qubits, so one qubit on either side. So I expect that you don't have time to read now all these things, but you can also pause the video later. So for each of these stages, one can actually identify some examples of known application protocol that already exist. And these stages, we like to find them useful for two reasons. Namely, A, they tell us sort of what do we need to do, sort of what does the hardware and the combined software and hardware system need to deliver. Basically, we want to go to an ever higher stage and increase technical complexity, while at the same time, it provides a challenge to protocol development to actually make a mathematical analysis that could show that maybe some of these applications that we already know can actually be realized in a lower quantum network stage that we know right now, but we just haven't analyzed that. So I want to give a very brief overview now about what is actually the state of the art of such networks. So maybe when you saw the abstract title of this talk, you went to Google and you Googled quantum networking, and you found out, hey, there exist large-scale quantum networks, for example, in China, connecting Beijing and Shanghai. So what's up with that? They seem to be long distance. It seems to be working right now. So these networks do not currently enable end-to-end transmission of qubits. Instead, they support a single application, namely quantum key distribution, i.e. the generation of encryption keys, but relying on the trust of the intermediate parties. So long-distance quantum communication is very difficult. So if you imagine that maybe Alice and Bob are too far to send qubits to each other, at least right now, but they have a friend, Charlie in the middle, that is close to Alice and close to Bob. They could use quantum communication to produce a key between Alice and Charlie, to produce another key between Charlie and Bob. And of course, provided that Alice and Bob trust Charlie, this enables them to now do end-to-end secure communication. So on this link, on this picture, for example, on the right, there's actually 32 such stations between Beijing and Shanghai. Of course, this means that anytime someone actually attacks such an intermediate point, also known as a trusted repeater, which is a classical repeater, not a quantum repeater, then security can be broken. So what we would like to achieve at QTech and also in the Quantum Internet Alliance in Europe is actually it goes beyond that. Namely, we want to enable actually end-to-end transmission of qubits and therefore also end-to-end security. So when thinking about where we are right now, it's interesting to think about this maybe in three axes, which I like to call functionality, accessibility, and distance. So accessibility meaning of how high is the JL level of this technology, how available is it to users, how cheap is it, can I buy one already? And on this axis, I would like to mention that actually at short distances, you can actually buy a box, for example, from ID Quantic or from Toshiba, and that does a single application called quantum key distribution. So this is something that is actually commercially available right now. So that does not have much functionality, meaning it can only do quantum key distribution. It does not bridge very long distances, namely only 100 kilometers, and also cannot be extended in a secure way. But of course, it makes the technology already quite accessible. So the question is now, where are we on the distance? So I'll explain to you later a bit why actually it's challenging to bridge long distances here. And currently the state of the art that quantum key distribution in commercial devices and deployed fiber is around 100 kilometers. In the lab, tests have been done to up to around 500 kilometers. Entanglement between quantum memories, so devices that can actually store quantum bits, has not been achieved at great distances, for example, in Delft at 1.3 kilometers, and more recently at 50 kilometers, but for nodes in the same lab. So some challenges are then not addressed yet in some very nice work in 2020. Entanglement has also been generated from space. So there's a satellite that has been launched into space that generates entangled qubits, and one is sent to one side, one is sent to the other side, that has produced entanglement over a distance of 1,200 kilometers. So this is super cool, but right now still too slow to actually do something interesting in a short amount of time. So this is where we are at distance. So you can see that my dot is very close to the origin. We're not very far yet advanced at distance. So how about functionality? So all kinds of protocols have been implemented, like quantum key distribution, and also things which are in the prepare and measure stage. Other cryptographic tasks, you can find them in our article, have been implemented at short distances. But I'd like to now mention to you actually a recent advance that we've undertaken in Delft, where we've constructed the world's first network linking 3 quantum processors in the lab. And this now actually provides the path to realize, at least at the short lab distances, certain protocols which are in the quantum memory stage of network development. So here we can produce entanglement between any 2 nodes. And also one can do a limited, of course, form of local quantum computation. So this is very exciting, and I'll tell you a bit more about how we use this later. So maybe to give a little bit of quantum background to understand also our link layer protocol, the world's first quantum link layer protocol that we've now demonstrated, is why is it actually difficult to break long distances? So, of course, this has a few answers, and quantum is, of course, different. But to be more specific, there's some differences which are fundamental, so they're inherent in quantum communication, one cannot get rid of them. And then there's some differences actually that relate to the technological limitations of present-day devices. So first of all, one cannot make a copy of an arbitrary quantum bit. And this is, of course, quite significant because it means that repetition, so, if I have a data qubit and I send it once, if it's lost during the transmission, I cannot resend it. Repetition is, in general, not a way to overcome imperfections. So of course, there's also technological limitations, namely that right now, the lifetimes of quantum memories that can store quantum bits and process them is relatively short. So in devices that have been connected to the network, so that actually have an optical interface, you can think that lifetimes cannot exceed seconds right now. Another fundamental difference between classical and quantum communication is that entanglement works quite differently. So when we do classical communication, we typically think of forward communication. I'm a sender, I send something, I send it to a receiver. The receiver can immediately start to interpret the data and proceed. And the notion of a connection, so to say, exists only much higher in a sort of abstract network stack and created between different computers. So entanglement works very differently in the sense that it's an inherently connected element already at the physical layer. I can only interpret entanglement, or I can only make it useful if I know who has the other qubit. And indeed, actually, we both are aware that we have created entangled qubits. So here we don't have this sense of forward communication, and I can also not make sense of my entangled qubit without knowing where the other one is. So I've mentioned entanglement already a few times now, this special property of that two qubits can have. And it's important to understand that entanglement here is actually useful for two reasons. A, it is actually something that quantum applications can use themselves in order to function, and many actually do that. But it's also useful in the networking context because it provides us a means to send qubits and therefore also contribute to bridging long distances. So how can we send qubits via entanglements? So you see here actually a sender and receiver, and we have created some entanglement somehow, let's imagine, between these purple qubits. And we now want to send this yellow data qubit. So this can be done by a mechanism called quantum teleportation. And if you come from classical computer science, it's maybe interesting to think about what resources and timing requirements enter into this picture. So teleportation is essentially a process in which a measurement is performed at the sender, which consumes the entanglement, and we are required to have 2 bits of classical forward communication from the sender on the receiver in order to enable the receiver to recover our yellow data qubit. So this idea of teleportation now also provides a very natural idea, or one of the ingredients actually in building a quantum repeater, namely by something called entanglement swapping. So let's think about this earlier situation where we had Alice on the left and Bob on the right, and say they're too far to send qubits to each other directly. But there's an intermediate box here in blue, which I will call a quantum repeater. And in order to bridge long distances, what they'll do now is something called entanglement swapping. So this means that the left node makes entanglement with the repeater in the middle. The right node makes entanglement with the repeater in the middle. And then we'll essentially use this idea of teleportation to create end-to-end entanglement. So if you want to think about it, let's think about this now as our yellow data qubit. And we'll, again, apply this idea of teleportation to now send this to the right node. So we'll make a measurement, and I will send it to the right node, thereby having created entanglement end-to-end. So again, from a computer science perspective, or if you want to build a network stack or any form of control system here, it's interesting to think a little bit about the requirements here. If the intermediate node has no memory, and I'll give you an example of this in a second, then in fact, this requires strict timing coordination. If the qubits don't arrive at the midpoint at the same time, then we cannot proceed to do this entanglement swapping because they're not both available at the same time. Or it could be that our quantum repeater in the middle actually has storage, meaning that we can try the left side for a little bit, and then we can try the right side for a little bit. But we store, and then we can wait until both qubits have arrived. So we don't need to have them available exactly at the same time because we can store them for at least a little bit a short amount of time. So this is actually what we've shown is possible in our 3-node network in Delft that is, you can find the link to earlier. So again, because this employs the same idea as the teleportation given you earlier, let me just remind you that indeed this again means also here that we need classical communication from the midpoint to the endpoint, and the original entanglement is consumed. So now you've maybe been wondering a little bit about, I gave you these boxes that have these, purple, yellow qubits in there, and I called them quantum nodes. And I don't know, what does that mean? Okay, so let me now maybe be a little bit more specific by giving you an example of a specific physical system that realizes such a node. And one such node is based on a system called nitrogen-vacancy centers in diamond. So this is a physical system that is very nice because it can both be used to perform local computation, but in the context of the discussion here, also has an optical interface, a communication qubit, technically the electron spin, that can be used to create entanglement with the outside world. So you can think of this network node basically, if you want to think about it more abstractly, as a little quantum processor that has a communication qubit, at least one. And this is what I painted purple here. And a number of other qubits, which we like to call storage qubits. Here in the specific example, the carbon-13 spins in the surrounding diamond material that can be used for computation and storing the qubits. So again, in this physical example, I also now want to explain to you how two of these nodes can be entangled directly. So we in our network, if you read our paper about a 3-node network, we actually use the entanglement swapping process that I already described to connect 3 nodes. So there we have memory at the nodes. But now the question that I want to discuss with you is, how do we connect 2 of them to begin with? And this is essentially the same idea, but it will only succeed with some probability. So let me explain this. So you see again our abstract nodes pictured here. So on the left side, we have the light blue node with the purple qubit. And indeed, you can think that physically, this is just this little diamond picture here with the purple electron spin. On the right side, we also have such a node with the purple qubit and the diamond material with the purple qubit inside. So this is what it physically corresponds to. So what happens now in physical entanglement generation is that trigger signal, so a laser pulse, is sent to the diamond device that creates entanglement between the qubit there at the node, just like in my earlier picture, and some traveling photons that travel to this middle box as already shown earlier. And then we use entanglement swapping to create entanglement between the 2 nodes. So in this case, the middle node, or node here, is not really a quantum node. It's just a simple linear optical element that has no memory. And this means that here one requires tight timing synchronization. So there's a little video of this. So here are the actually communication qubits, i.e. electron spins in the device. And first, a trigger signal is sent. So this needs to be synchronized in time to arrive actually at both nodes simultaneously. Now entanglement is created and traveling to the midpoint station, here indicated by this plate beam splitter and detectors. If the detection is successful, then we've made end-to-end entanglement, indicated here by the line connecting the gluons. So this was, an ultra-fast introduction to quantum networking and how it can work. And I now want to use the remainder of the time to get back to this question. So how do we go from such a physics experiment to an actual network system? And what I want to discuss with you is the world's first quantum link layer protocol that we introduced a few years ago, and that we have now, however, implemented on hardware. And I'll show you some brand new results of that. So this is joint work with quite many people in my own research group at QTech, with my hardware collaborators, Ronald Hansen and his group, our extended software team at QTech, as well as people who support us to actually manage such large projects. So indeed, I will present a quantum link layer protocol, and I suspect that most of you have heard about what a quantum link layer protocol is. But if not, let me just give you an example of this. So you see here a plug that is probably known to most of you, namely Ethernet plug. So classically, Ethernet is a link layer protocol, and its objective classically, as well as the protocol that we'll be discussing now in the quantum regime, the objective of such a link layer protocol is to take a physical communication medium and add some things on top, such that it becomes a reliable transmission service where also anything on top of that, say higher up in the stack, does not need to know anymore how is this physical transmission actually realized. And we do this now also for quantum communication. So we've introduced a quantum network stack in microbit QTech that looks very similar to the classical domain that distinguishes a physical layer, a link layer, a network layer, transport layer, application layer. So let me maybe say a little bit more what this means. So the physical layer is the physical device layer that we've just actually discussed, where I showed you that in the video. And for the purpose of this discussion, remember also what was required there. So it will be the task of the physical layer to produce the physical entanglement, meaning we make an attempt to produce entanglement. So we send a trigger signal, photons travel to the midpoint, we may succeed or fail. So this means that this physical layer entanglements, at the physical layer, we will have tight timing synchronization. So we have hard real-time requirements at the physical layer in order to produce entanglement, and we don't always succeed. So on top of that, we want to add something which we will call a quantum link layer. And the purpose of the quantum link layer is basically to make this physical device generation robust, and also ensure that anything on top of higher up in our stack does not need to know what is this physical platform that we actually, what is the physical hardware that we're using to produce this entanglement. So higher up is so the link layer is responsible for basically providing a robust entanglement generation service between two nodes that are connected directly by a link. And the network layer is, like in classical TCP/IP, responsible for producing entanglement between two nodes that are not directly connected, for example, via this entanglement swapping process that I presented to you. We can think about a transport layer to do end-to-end qubit delivery, as well as, of course, at some point, again, add quantum application protocols that can run on this combined system. So I will be concerned only now with what's in the red box at the bottom. So we've already discussed the quantum device layer, and I now want to first explain to you actually what is the service, so to say, what the link layer now provides to the higher layer. So our link layer, or our quantum entanglement generation protocol, aka QEGP on this slide, the service that it provides in a somewhat simplified form for the purpose of this talk is that from a higher layer, you can say, create, please make entanglement for me, to specify a certain number of entangled pairs of qubits to be produced, or a rate, a minimum fidelity, so a minimum quality that this entanglement should be having, a maximum time that I want to wait for it, and so forth. So the link layer will then interact with the physical layer, of course, to make that happen. I'll say boring parts in a second. And then eventually, if entanglement has finally been produced, so indeed we might need to make several attempts at the physical layer, remember, then the link layer will say, okay, I've produced entanglement, and importantly also produce an entanglement identifier. So that allows the higher layers to immediately consume this entanglement without requiring any further discussion. And that's quite desirable here because quantum memory lifetimes are short and we want to proceed immediately. So when thinking about such protocols, it's maybe useful to know about what defines a good protocol. So what are our performance metrics? So of course, you're probably very familiar with classical metrics or standard metrics like latency and throughput and fairness, and one can define them all here as well. So we can think, for example, about throughput, like the number of entangled pairs per second. But in the quantum regime, there's a very important quantum metric, namely the fidelity or the quality of entanglement. So it is actually not the objective of our network stack to deliver noise-free entanglement to the application, like one wants to do noise-free communication in the classical world. And the reason for that is actually that quantum errors can be corrected in an application-specific way at the classical layer. In many cases, that does not need quantum error correction. So for example, in quantum key distribution, one can use classical error correction at the application layer to eliminate these quantum errors, and therefore one is perfectly happy to have also imperfect entanglement. It's interesting maybe to know that this fidelity, so the quality of the entanglement, has interesting trade-offs with the other standard metrics. So I can, for example, choose to have a higher throughput and a lower fidelity, or I can have a higher fidelity but then have to accept a lower throughput. So if one designs such protocols, it's a little bit user instructive to think about what should we actually be doing here. So what are the use cases or requirements that one would want from such a protocol? And there one can distinguish actually some, maybe two broad ones that come from applications and also network layer use cases. One of them, which we call measure directly. So this means that actually we're reproducing very many pairs, but the end nodes measure them immediately. This means that, in fact, no quantum information is kept. So this corresponds to a highly, in fact, elastic application where the jitter, so the time between delivering different pairs, is essentially irrelevant. In the other contrast to that is what we call create and keep. So this corresponds to applications, or actually also the network layer for entanglement swapping, that needs several pairs to exist at the same time in order to function. And at this point, the jitters, so the inter-delivery times, become extremely important. So if you're curious actually about this, it's quite fun and interesting to think of such protocols because they employ quite an interesting mix of computer science ideas, but also some concepts actually that come from the physics of the devices, at least at the link layer. So one is actually quite easy, namely that noise is time dependent. So waiting is expensive. Like, if you wait too long or memory lifetime is short, it's only seconds, the qubit will decay, quality will degrade. So this, as a consequence, means that actually one wants to avoid having to wait ever once the entanglement is actually produced. So this means that unlike in the classical world, it is actually quite often interesting to have a lot of prior discussion before we make the entanglement, and then discuss as little as possible afterwards. So this is quite different than classical networking, which usually just goes ahead and then recovers if things go wrong. So it's also interesting to note, actually, this comes from the physics of the devices, that triggering entanglement, so if I shine this laser on the little device, then in fact this causes noise on the qubits which are still in memory. And this means that one wants to avoid triggering for entanglement generation, unless actually I'm very sure that the other side is also triggering in that time slot and we agree to produce entanglement. Because otherwise, I just destroy my local storage for nothing. So this means that one wants to achieve some a priori agreement or coordination before we actually start producing entanglement. The last one is motivated by the fact that, again, we are looking for solutions here which use the simplest possible quantum devices. So note that quantum communication is trivial on paper, namely we are just going to bury a quantum computer in the ground every 5 kilometers, and then we use error correction involving millions of qubits. But we don't want to do that here. And in particular, this means that in our link layer protocol, we also don't use any error detection, as for example, in classical link layer protocols like Ethernet, because we don't want to add redundancy by adding extra qubits, which are prohibitively expensive to implement. So this means that instead of adding such, say, quantum checksums, what we do is actually we intersperse test rounds. And then one can prove a little theorem that using these test rounds, one can actually make an estimate of about the quality of the entanglement in the non-tested rounds. Okay, so I'll explain to you a little bit about what the protocol looks like at a super high level. So basically, let me just take you through this. So we start at the higher layer creates ask for entanglement. The first thing that we do is we achieve some agreement with a remote node. So in our link layer paper, if you go and look it up, this is achieved using a distributed queue. In our implementation later, actually, we now use a centralized TDMA scheduler. But the objective basically means that we'll first achieve agreement with a remote node. So then, we schedule basically a demand for making entanglement with certain parameters depending on the fidelity requested. Since the physical layer, as already explained, requires tight timing synchronization, so these are hard real-time constraints, the physical layer actually dictates when what happens, meaning that it will actually poll the link layer and ask whether in some specific time slot it should issue a trigger. If yes, then it will go ahead to produce entanglement, like the video that I just described to you, and convey the result to the link layer. If the result is negative, i.e. no entanglement has to be made, then we need to try again. But if it's positive, then we can send an OK back to the higher layer. So this is in, sweeping very many things under the rug, how the link layer protocol functions. And brand new, I'm very happy to announce that actually we've now, just recently, now implemented it on actual quantum hardware. So this is what such an actual implementation look like. I'm quite sure that we cannot go through all of this now in this talk, but in the bottom you can basically see the diamonds. There's a lot of hardware that is needed to actually control the physical devices, including, for example, like the laser pulse that I've already mentioned to you, as well as microwave pulses controlled by an AWG. So on top of that, the link layer runs currently on a dedicated microcontroller that implements actually the protocol that I just described. Maybe the only thing I want to highlight now for the purpose of this talk is this little piece where I zoom in. So I say here a physical layer driver, where I say here NV for this NV in diamond, so nitrogen vacancy center in diamond that I mentioned earlier to you. So this is quite flexible, so our implementation can actually also work with other systems, for example, ion traps. And indeed, we've achieved the objective in the sense that above the link layer, higher in the stack, we don't need to know now anymore whether the underlying technology used at the physical layer is now actually, for example, nitrogen vacancy centers in diamond or actually ion traps. So this means that also network layer protocols and higher layer protocols can now proceed without that knowledge. So in the interest of time, I just want to show you two plots. One of them is about this performance metric, actually, that I just explained to you. So quantum people care a lot about this fidelity, i.e. the quality of the entanglement. And you can find here at the bottom the requested fidelity, so this the create request, and the measured fidelity, which is the blue dots here. So we're actually a bit cautious and optimized for a slightly higher fidelity. So you can see that actually our combined hardware software does deliver on the requested fidelity. So maybe it's just interesting to understand what are the latencies here. And the specific thing that is very interesting to understand there is what is the overhead incurred by the link layer. So this plot actually shows, in a sense, the maximum overhead, in the sense that per create request, we only ask for a single entangled pair and not multiple at once. And that's kind of important here, because this means that for every single pair, we might have to wait for the right time slot and therefore introduce more delays than we would actually see if we would ask for more requests. So this is, say, the maximum pessimistic plot, where you can see sort of where the latencies for requesting different fidelities. So this shows you that there's an inherent trade-off between these two metrics, so the fidelity, quality of the entanglement, and the latency of delivery. And it also shows you a bit of where these latencies actually come from. So you can see actually that the latency is vastly dominated here by the physical layer, where the link layer part is relatively constant, where actually the interface part, so meaning how much communication overhead is there between the physical and the latent, and the link layer becomes more significant as the fidelity increases, which is also to be expected there, because actually it takes us much longer to make a higher fidelity link, because lower throughput, higher fidelity, lower fidelity, higher throughput. Okay, so if you want to learn more about this fascinating new area, you don't have your own hardware, but you still want to explore some applications, we have a little simulator for you that you can install actually on different computers, and you can then go and program your own quantum network application if you want. We also have a much more detailed simulator that does not run in real time. That is a discrete event simulator that you can use to learn more about quantum networking, and that can be used actually to study both designs for communication networks, but also modular quantum computing architectures. So you can download it actually at the URL below. I also have a MOOC online if you want to learn more about quantum communication, specifically quantum crypto. And if you're interested to learn more about the activities of the European Quantum Internet Alliance and our partners in this project, you can also find more information if you pause the video and look at the URL above. So thank you very much for this talk. And if you have any questions, then please also feel free to drop me an email whenever convenient. Thank you very much.
All right. Thanks for coming to our invited talk session. If you're interested in more invited talks, at 1:30, we're going to have 2 sessions on HPC for COVID and a panel on diversity in HPC. So hope to see you all there. Thanks.